Hi, I'm Jonathan Harris at nTopology, and today I'm going to show you how to simulate lattices. Very, very big lattices with a technique called homogenization. So today we are going to cover what is homogenization, when can you use it, when can't you use it, and how do I do it from a blank screen in nTop. Okay, to start, imagine simulating this 1 million unit cell lattice. It would be a nightmare with volumetric elements, shell elements, whatever elements you want. You can't really do it. This would take millions, tens of millions of elements, maybe more. What homogenization does is it takes a single unit cell and characterizes how that would behave in isolation. And that's good because you cut down the simulation from one of millions of unit cells to one of it's just another material. In this case, an orthotropic or anisotropic material. So these colorful blobs, they indicate the stiffness matrix of these materials. This is why we call them architected materials, because you're architecting your material properties. So we see people taking titanium, for example, which they can print confidently, and they want to modulate the material properties to, say, behave like bone if it's going into a medical implant, or improve the thermal conductivity of titanium by increasing the surface area or what have you. So homogenization is a way of quickly predicting how much these changes will have an influence on. It's not a final design accuracy method to replace those simulations. We have to make that very clear. It's just a method for the initial designs. So again, nothing comes for free in engineering, so that's the limitation. But where it's good is sorting out the overwhelming decision of all of these different geometries, all of the different parameters within those geometry families, like strut angle, strut thickness, relative density, all that sort of stuff, and helping you come to a few candidate designs a lot quicker. Okay, so we could go on about that for a while, but the point of this is really to show you how to do it in nTop. So the result that we're going to chase here, here's a file already done, but we're going to do it from scratch. This colorful blob indicates the stiffness properties of this cubic unit cell. And you can see, okay, that makes sense. The stiff bits of the matrix are aligned with the beams. And if you start to triangulate that structure more, like in this octet unit cell, you get a totally different response. And of course, it's more triangulated, so you get a more uniform or more isotropic response. A brief primer, if you're wondering, what is the stiffness matrix? What are you talking about? Okay, not to scare you, but just Google Hooke's law and you'll see the whole thing here. So this is how the materials are stored in the system. If you're just dealing with materials off the shelf, you're going to see Young's modulus. If you're dealing with complex materials, that starts to grow and you get different stiffnesses in different directions. So that's why it looks like a big matrix. In nTop, we will analyze whatever geometry you throw at it. So it's built to handle that full complex material. Okay, to start. So homogenization, anything you put in a box can be evaluated as a unit cell and used as a unit cell. So to start, let's make a box. And we are going to, tough decision of which unit cell to choose. I think we'll do gyroid to start. It's the fan favorite. So we will start by making one unit cell, because what we're going to do is treat this one unit cell. You can almost think of it like a grain of that material, or like a fiber of that material that we're going to be replacing. So, or that we're going to be simulating, rather. Okay, so I've got a unit cell here, and we still have to mesh this. We still have to do a simulation on this in order to get the material properties. So what I'm going to do is mesh this. So if you're using nTop, already, there's a lot of different ways to mesh things. We're going to start with the frontline approach, just getting a nice exterior surface mesh. If you have a really nasty geometry where this is giving you errors, you can try out the voxel grid mesh, voxel grid from implicit. This almost does like a 3D snapshot of your geometry, and it should capture it without errors. So mesh from voxel grid. So if you're struggling with this method, and we'll see if this works for me, you can do this, and you'll just replace that step. Okay, and I should probably name my file too. Homogenization tutorial. Can't spell when you're doing it live. So, okay, so we've got this mesh, and we are going to turn it into a nice simulation quality mesh. So I'll just make this a variable, unit cell. We're going to take this kind of ugly mesh and remesh it. I'm just picking one to start. We'll see how that turns out. Now, I actually picked the gyroid because it has a little quirk in it. It has these floating bits. So we have to remove that, and I figured it would be a good thing to show you how to do that. So this mesh is actually comprised of 3 different bodies. You can see when I split it, it tells me, hey, there's 3 of them here. I'm going to build this workflow to be repeatable so that I don't have to care if there's 100 broken ones or floating bits. I'm going to build that into my homogenization workflow. So, filter, mesh, list. You can see it comes with a list. We're going to put that in. If I pop this open, again, you can tell it's a list because it has that number next to it. I'm going to open this and see, oops, face count. So you can see, here's the big one, 71,000 faces. That's got to be this. And then the little corners are the small ones. I'm just going to guess the number, and we can come back and revisit this after, that I want to narrow down this list to only include those that are above this value. So this will eliminate those little bits. We'll test this after as we change our geometry to see if it's robust for anything that you throw at it. Okay, so commenting that, remove floaty bits. And okay, so this is now a list of 1. Again, nTop is built so that it will replay the workflow. If this were a list of 1 as we have it, we want to come in and grab that single chip. If I change this, it could be a list of 100, so that's why you can't just drag this guy right in. Again, that's indicated by the number in brackets. Okay, so this, we have a simulation mesh, but there's some ugly triangles, so we're going to play with these parameters. One thing I like to do, especially if there's any mesh errors, is start by looking at this minimum feature size. That is not the minimum edge length, that's a different value. Minimum feature size, you can read here, small feature size to control the deletion of small features. So what this does is it comes over through this mesh, and it will see, hey, that's a pretty ugly sliver. We're just gonna pave right over that. So as it recommended there, you can make it a fraction of your edge length, and it should start to clear things up a bit. Looks like we could still work on it. So I'm actually going to make this a lot smaller, and we're going to also put a minimum edge length because I'm not liking those small triangles which are appearing there. So again, we're not escaping meshing here. We're still having to mesh this unit cell, but we don't have to mesh a million unit cells. We only do this for this one unit cell. Okay, so it looks like I still have a bit of ugliness in my kind of cool about nTop, you can actually keep working as it's doing the computation. So I'm going to make my next block volume mesh. Okay, this is looking a little better. If we wanted to, we could come in and keep working on this. I would probably look at the growth rate or feature angle for these. But again, just for demonstration purposes, this should be pretty good. So we've got a surface mesh. We need to fill it with volumetric elements. So I'm just going to match my edge lengths here so that they're nice and uniform. 0.5. So this will fill it up. You can actually now, in nTop, press X, and you can see what that looks like almost as if it were like a rock, and you break away the grains, which is kind of cool. You can see the tets inside are pretty nice. We're going to come back later and make them smaller just to capture any deflections within those thin walls, but again, just for starter's sake, this should be good to go. So as the pink color or orange color suggests, this is just a geometry mesh. We actually need to make it a simulation mesh. So what that does is it assigns the basis functions to these elements. So we will select a nice quadratic mesh here, and I'm going to make this variable because I'm going to use it a lot. That's a good tip in nTop. If you're going to use something repeatedly or refer back to it, make it a variable. It'll make things a lot cleaner. Unit cell. Okay, we're moving now. So simulation in nTop. It can be a little daunting, so I'm going to show you how I do it every time. You can do it in two directions, which is kind of cool. Adapt it to how you want to work. I'm going to do it in direction which makes sense to me. So you could click the buttons and work your way up by making this mesh into a solid model, assigning a material, making that into a FE model. But we're going to go a little backwards because I think it makes more sense. So I know I want to homogenize, so I only search for that. But if you're stumped here, this is where my double-click trick is so helpful. Just double-click the empty input. It's going to suggest to you what are the acceptable inputs here. This is a solid model, so I'm going to pick FE solid model. Okay, it's asking me for a solid mesh. Double-click. Hey, here's my suggestion. If you hadn't made this already, it gives you a list of all the different things that you could try. This little icon means that it exists. You can see those icons match. So I'm going to put it there. Material. Okay, let's pick our material. If you want to use nTopium, which is my name for a material where all the properties are one, you can do that too, just to help pick your unit cell. This material doesn't really matter too much right now because we're just trying to pick the unit cell. And this only considers linear behavior, so it doesn't really matter too much. Why don't we pick rock, paper, scissors, T6. Okay, so we have a unit cell. This little gyroid is aluminum. We need to tell it what box it is inside. And that sounds a little trivial, but all you have to do is actually refer back to this box. And you can see I'm dragging it and I press Control, and that actually makes the little plus sign appear, so it doesn't take it away from that block. And now it's running. So what it's doing, if you look closely here, it says solving 5 of 6. There's actually 6 different loads that it applies to this unit cell, almost like an experimental test. And what it's doing is applying the principal directions and shear cases, and it's evaluating how is this material behaving. So I'm going to make that unit cell homogenize, or a variable rather, homogenized result. Click this, and you can see it has done some sort of simulation. If we check the displacement box, you can see the various loads that it applied, X, Y, Z, and the shear cases. And from this, it can reconstruct that whole stiffness matrix, which you saw on this page, or if you don't care about that in particular, you can see it in the blobs here. So the blobs are visible by switching to directional. And now you can see a representation of your lattice's mechanical behavior. And it looks here like the gyroid is actually very, very close to isotropic. If you look at the bounds, 1.4-ish to 1.2 between the red and blue, that's pretty uniform in terms of how unit cells go. So if you did a honeycomb, for example, you can see, okay, that's only going to be stiff in this vertical direction, which is obvious. It makes sense for that to be the case. So there's sometimes when you know where the loads are coming from, where you can really benefit from just a stiff uniaxial unit cell, just like you would a uniaxial fiber in a composite. But there's other times where you're not so sure where the loads are coming, or they're more complex and you might need something more isotropic. Okay, so we've got our unit cell. I think I'm going to save the file just at this point. So let's see how robust my workflow is. That's why I saved first. So if we change the unit cell from a gyroid to, let's do diamond. So very, very different unit cell. It still has the floaty bits, so let's see how my removal works. Yeah, it looks like it actually did remove those. If we're treating this as a material, we don't really care about the floaty bits because it's going to be adjacent to a whole bunch of identical neighbor cells. So this will actually be carrying over into the next unit cell and you don't have to worry about it. Now you may be thinking, hey, this looks like multiple unit cells within one box. You can homogenize whatever you want inside a box, and actually if you homogenize more than one unit cell, you can get a little bit better of an idea of how things will perform because it considers something called edge effects. And that is really the limitation of homogenization, is that those 6 loads assume that your material is in an infinite array of a lattice. And that might be an okay assumption for something like this, but it's not going to be okay. You know, it might even be somewhat okay for this, but it's not going to be okay if you only have a handful of unit cells across the side. I realize I have it in highest res, so we're waiting for a render. It's not going to be okay if you only have a couple unit cells. This is the same principle as you would have in something like a fiber composite. You're not going to use the individual carbon fiber strength to represent a laminate. You need to use some approximations to knock it down. Okay. Let's go back here. So just like all the other engineering models in the world, things like aspect ratios on beam approximations, there's limits on when you can apply homogenization. In general, you need a lot of unit cells. And the reason I haven't given you a number yet is because it's kind of an unsettled argument, and it varies by unit cell. A general consensus, just to give you ballpark, is, we're talking about tens of unit cells to get an accurate response. But this will vary by unit cell, so I don't want to say, hey, ten's what nTop said to do. You're going to have to do some sort of convergence study to see how accurate that approximation is. But if you were listening to the first part of this video, you're only going to use homogenization to tell you which unit cell is better anyways, not which one is good enough. There is a difference. I can say that a gyroid is better than a diamond unit cell in this case. I I can't say whether it's 10% factor of safety on my life critical component. So there is that limitation. Okay, so it looks like diamond is pretty isotropic too. It's nice. Let's see what happens when we intentionally skew it out of plane. So what I'm going to do here is stretch the unit cell up. So let's say you wanted a little more stiffness in this direction. Let's just smear the material in that direction and see what happens. So we've kind of skewed it out of plane, and it's going to be rerunning. It actually remeshes all this, it reruns, and we're talking about a couple seconds, which is pretty nice. Let's see. So remeshing, about 6 seconds. Let's see how this goes. What's nice is that some of our users have actually linked this up through our batch processing. So they list out a bunch of different configurations and power through them through a script. That's a different how-to video, though. Okay, how long did that take? So with meshing, 35 to 40 seconds, pretty good to get you a quick answer. Okay, look at that. So we get a lot more, almost double the stiffness in this direction than we do in the side-to-side direction, in the in-plane direction. So that's kind of cool that we can tune our material to fit a functional purpose. So let's say I have this material now. How do I use it? So you can use the homogenized results either in nTop or in external tools, which is really nice. You can actually do your unit cell design in nTop and then run it in Abacus, for example. I'm going to show you both. To start, which one should we start with? Okay, let's export them. So export material. You can see this geometry, it actually is treated in our system as a material. So how cool is that? This is treated as a material in nTop. Pretty neat. We need to specify a path. You can see it tells you the different input deck types. There's also just CSV format, which I believe will give you the stiffness matrix raw. So test material. Okay. Just need some units. We're just going to pick the defaults, and now it will appear. Check it out in Notepad. You can see, hey, it printed my anisotropic material in Abacus format, which is kind of cool. So you would just copy paste this into your input deck if you're running Abacus. Let's see what it does if we do a CSV. So test. Okay, nice. So this is the 6x6 stiffness matrix. So see, 6x6. And if you wanted, you could go and visualize this in MATLAB or what have you. But here's 2 export types. You can do that for a bunch of other ones too. Okay, how do you use it in nTop though? So we'll delete that export. This is actually used like any other material in nTop. So to demonstrate this, I'm just going to do a very simple cantilever beam just to show you how it's laid out. Maybe you've seen some nTop simulation tutorials already. Not meaning to replace that, but I will try to explain a few steps along the way. Again, we have to make meshes, which I say not so pleasantly. In this case, I'm not going to remesh this because it already is pretty good. I'm just looking for the elements to be somewhat uniform, and they already look good because it's just a box. If you wanted, you could put a remesh block in between. Okay, so we're going to go match the element sizes. And we can double check this with our show volume elements. This is good enough just for example's sake. Again, we need to put some FE characteristics onto these tets. And we will just continue, apply some loads. So again, I'm going to use my trick and work through the double click. If you wanted, you could build it up the other direction, but honestly, I forget what to do when I'm doing live videos, so I'm going to just let the double click guide me. Cantilever beam. Okay, materials. So we could put aluminum, or we could put our own special TPMS brew. So why don't we do aluminum to start? Just to show the difference, and I'll just make sure I get the same alloy that we used. Okay, we need some boundary conditions. Again, we're going to keep this simple. Displacement on one end, force on the other. Boundary, there's a few different ways. FE by body sounds good to me. We're going to pick the target mesh. Again, I'm jumping through this because there are videos on how to do simulation, but maybe this one can be a reminder. So you can select nodes really easily in nTop. You can do it with any implicit. So I can drag around this box and it will programmatically select the nodes. So if you change this to a brake pedal, it will still select the nodes there. It's kind of cool. I'm going to use a plane on either end of the beam. So this plane, I will make it point in the X direction. And I'm going to link the origin to the size of my cantilever beam. So if you go into this, you can find the properties. You could just put 25, but I'm going to try to do it so that if I change the beam, this workflow would still update. That's what I always like to do in nTop, is do the hard work once and then be able to reuse your files. So you're almost building a little program as you go. So if you can build in some robustness as you're going, that usually pays off in the long term. We're going to do that again. Nodes, body, we're going to put a plane on the other side. It's going to point right one. So we could go scroll back up to the box, but if you don't want to do that, you can click the little plus sign, and you can actually do it in kind of a programming way, where you'll press that, press the down arrow, and you see all this stuff gets revealed. And you can go further in if the input accepts it. In this case, it's looking for a point. You can see that here. So if I select these, it won't accept that. But if you select the right one, the appropriate input type, it will update. And so we've got both ends selected. Let's just use any old force, 0, -10. And it's going to run this analysis as if it were just our normal aluminum. Okay. So no surprises here. The beam deflects downwards. But what we're going to show is that, remember this number, 7.16. So that's the deflection at the end of the beam. We're now going to replace this material with our homogenized type. So homogenized. We could come up with a better name for our material. But it's running this now as if it was treating the entire beam as a continuous diamond TPMS. And you can see, wow, what a difference that made in our deflection. It obviously deflects a lot more because we took out a whole bunch of material. Let's remind ourselves how much. If you click the question mark, it says this is 37% relative density. That means it's 37% the weight of the solid material. So you can start to do that trade-off analysis of, okay, this type of material does 37% of the weight, so not 37% lighter, 37% of the starting weight, but it gives me that difference in deflection. Let's just save this again, and I wasn't really planning to do this, but why don't we just switch it out again, make it a Schwartz, and just see if the whole thing updates. So this is going to be almost, it almost looks a little bit like a honeycomb. We can see our floaty bit deleter, that worked all right. So I think the 1 was actually a good guess. And it's currently homogenizing the unit cell, and then it will go right on to analyze that in the beam. If you want to use this file, we're going to attach it to the to where this video gets posted, and you can certainly try something more complex than a beam that you can put in here. Use the And if you're feeling really daring, you can try homogenizing, or you can try running a non-homogenized analysis on your full part. So that would entail meshing thousands of gyroid unit cells, and it would not be pleasant to do that. It's always funny to see what kind of blobs you can make out of homogenized material. If you remember this screenshot, there's some pretty interesting shapes that you can come up with, and those shapes represent the mechanical response. Okay, so we're going back to our beam, and you can see that one, that Schwartz is actually a lot stiffer. I think the previous one was 4. And that kind of makes sense because it does look more honeycomb-like. So you'd expect it to have more bending stiffness in that direction. And just Control-Z-ing to make sure I got that relation right. Yeah, so 4.8. So it's about half. Okay. So you can see I'm going through this, I'm kind of designing a material as I go. I'm not saying, hey, this is my final part. I'm just making decisions of, maybe if I want bending stiffness, I'll think about a Schwartz rather than diamond. There's a lot more cool things you can do with homogenization, which I would say stay tuned for. So things like electrical and thermal properties, some of those can be homogenized, so you can start to do this analysis, this type of analysis with multiphysics, which is pretty exciting. So you're designing on an Ashby chart, not of stiffness and density, not just of stiffness and density, but also thermal conductivity and stuff like that. So there's really a lot of potential with this technique, but again, I have to mention the limitation is how many unit cells do you have? And maybe you were thinking about this when I showed this. It's like, okay, here's a beam that's pretending to be our Schwartz unit cell, but how many unit cells are in it? And the answer, unfortunately, is infinite if you're assuming homogenization is doing its thing. That's not really an acceptable answer to engineers. It might be for mathematicians, but we want to make real structures, so we need an answer better than that. And homogenization doesn't actually consider whether it is this structure or whether it's this structure. It doesn't make that decision for you. That is up to you to make the right assumptions. So as powerful as this technique is to help select a unit cell, I do have to caution against using it to do final designs. So if you have enough unit cells in your structure, this one, maybe you're getting away with it. Again, you'd have to do that convergence or sensitivity analysis. Then maybe you can use it to go a little further in your design. But really, it's a great way of making those initial trade-offs in picking the right unit cell. Okay, so thank you very much for if you're still watching this video after all those minutes of nerding out on homogenization. If you have questions, please either leave them in the comments below or contact us at what's our email again? info@ntopology.com. I might change that and put the right URL up, but yeah, feel free to contact us. Any questions with homogenization or making these architected materials do things which your conventional materials can't. Thanks.